It's, of course, a great pleasure to have Sabrina Pasterski here, who she's going to be telling us about fun with celestial dressings. So take it away, Sabrina.
Okay, nice to see you guys, and I'm happy that you're able to enjoy coffee breaks with one another. I mean, I wish I were there. Some with the traveling and not able to be there, but that's nice that things are turning back around so that we can have in-person celestial holography gatherings. So I hope you enjoyed your coffee break. Post-break, the topic is going to be fun with celestial dressings. And so the title is a bit whimsical, Harbingers of Chaos, Heralds of Symmetry. And it will be accurate with respect to the kind of moral of the story that I want to convey, given what I'm going to present, which is actually a paper from December with Herman, which in practice, like for the particular computation in that paper, that's going to be the majority of the talk today. It's not really very celestial holographic, but it's using the same starting point with these soft theorems and the HPS hair story. So what we're going to basically do is try to look back at that paper, and it's been a while since I've, I guess, presented to some of the people in the audience, and I don't think I presented it to everybody, with the lens of kind of what we've learned with Andrea and Emilio and Yorgo regarding these like celestial diamonds and this conformally soft sector from the celestial CFT. So the point of this talk will be to just present that the results of the paper with Herman, and then put it in the context of the lesson that you learned, given what we know now with what you were hearing about yesterday from Andrea. So at Corfu, and then also yesterday, Andrea presented the celestial diamond story, and then even how they stacked into the celestial pyramid, introducing supersymmetry. And so we saw that the punchline of that talk is basically that all of these different notions associated to infrared physics get captured just by even doing a systematic treatment of the global primary descendants. So you can get a lot from something rather simple, and then pushing through it, you can see nice connections between various current statements and OPEs, effective field theories, dressings, this BMS flux story that you heard like that opened the workshop with Laura, shadow relations between currents and certain like soft modes of the gauge fields, and so on. So basically, you have the structure that Andrea pointed out yesterday that connects all these stories. And the interesting thing about it is that those stories are also going to be major players in this other, basically somewhat seemingly unrelated, the story of how to use the soft hair on the horizon to evade a firewall if you're an infalling observer. So basically, the thing for today, the main actual like topic for the talk today, is that I'm going to revisit this Hawking-Perry-Strominger proposal from a while back now, and try to merge that with the celestial CFT perspective, because in the end, like we are building this holographic dictionary, we want to be able to say something more than just compute scattering matrix elements. In the end, even like the way the S-matrix program would be set up is that you want to know about interesting bulk physics. So what's happening, not just like what is the scattering amplitude. And so that question in celestial CFT is pretty much like building up what's happening in the bulk from the boundary. And even though the phrasing of this paper isn't in terms of celestial CFT variables, we're going to see that the same ones that were kind of the key players in the talk that Andrea gave yesterday are going to be playing a role here. And so we basically want to motivate a kind of like outlook towards how to try to start saying interesting things about bulk physics from the celestial CFT, given the part of the celestial CFT that we have maybe more control over, which is the soft sector. So the theme of the talk today is, let's see how we can merge these interesting questions about celestial CFT and the conformally soft sector with ones about like what's happening in the bulk. And in particular, the starting point is, of course, the symmetries are playing a very major role in this story. So like everything in the celestial diamonds, there's a current somewhere in that diamond that you're looking at, whether it's at the top and you're talking about this W infinity, or at the left and right corners and you're talking about soft theorems, or at the bottom and you're talking about these BMS fluxes. These symmetries are the major role. And we know that there's already been a very nice lesson learned from these asymptotic symmetries that was going beyond just this ward identity asymptotic symmetry soft theorem story equivalence, which was this very nice result by Hawking-Perry and Strominger, and Hako and others have built on it too, where you can talk about how those asymptotic symmetries also, there's an analog at the horizon, and what those constraints imply for interesting like black hole evaporation or other processes. So the moral of the story is going to basically be that we're going to see that the dressing modes, which are at the top of the celestial diamonds, are playing kind of the key part of the argument in this paper with Herman. And so as much as like in practice, the talk is just going to be about presenting that argument, we want to distill from it kind of the sense in which it's really the dressing that's the key player here, and then kind of see from that setup how one might try to push forward with other interesting bulk phenomena in the celestial CFT context. So that's going to be the theme of the talk, but in practice, we're going to actually present the story from HPS. So I think, like, as far as the audience is concerned, I probably given the full presentation of this HPS meets AMP story at a nice group meeting in December or January, January. But it's been a while, so hopefully now we have more context for that. So basically the point of that story is that we are talking about how to merge the story of this Hawking-Perry-Strominger soft hair and black holes, how like the fact that you have these infinite dimensional symmetry enhancements that also constrain black hole evaporation or scattering in the presence of black holes, and how we can basically plug that into resolving a tension pointed out by AMPS, which is that there's a tension between the fact that you would expect from Hawking radiation to smooth horizon that you continue to generate entanglement, but from monogamy of entanglement, if you're post-page time, the entropy should be decreasing. So basically, now like that story on its own has had a lot of people approaching it from maybe some quantum circuit technology, et cetera. And so basically there's certain building blocks that one would like to kind of plug in this soft hair interpretation into, and then one can say, oh, look, we can study the experience of an infalling observer using the fact that there are these IR degrees of freedom. So the setup is trying to merge that by basically coming up with an interpretation of existing quantum circuit technology that would provide this quantum teleportation protocol to allow you to have the right entanglement structure from this soft hair. And the moral of the story is going to be that you want to argue that an infalling observer will end up making a measurement of the soft hair, and that soft hair Hilbert space is large enough so that you end up being able to do the appropriate quantum circuit manipulations to have the right entanglement structure and therefore be avoiding a firewall. So that technical part of the setup isn't going to be the main focus of the talk, that we'll get to those ingredients. The main thing is going to be basically how that measurement can come about from different properties of the soft hair phase space. So in order to make the argument in the paper, there are basically different steps, like 4 different steps that one has to follow. The first thing is you need to understand the soft hair phase space, and note that that means, from the point of view of celestial CFT, understanding like essentially like any like in and out labels or horizon labels for each of your Goldstone mode operators. Then we want to explore the entanglement structure between the observer and the soft hair, and that's going to not really be celestial at all at that point. We're going to motivate the installer, we'll measure the soft hair, and then finally, those are the ingredients that you build up to then apply existing quantum circuit technology. So basically, Yoshida, its papers that we're using there, to this HPS paradigm, which is this interpretation of the soft hair. So that's the route for that paper. And basically, the following assertions are what you need, or at least like this is enough to then argue for that applicability of basically the soft hair phase space being able to be a way to interpret the different, I guess, like we'll see the quantum circuit, the different sectors of like that Hilbert space, as well as the entanglement structure via the fact that we have these properties of soft hair. So let's just go through them 1 through 7. Okay, so the fact that basically the soft hair is some sort of measurable feature of the global black hole space-time that would be invisible to, and I'm saying the hair at the horizon is invisible to a strictly asymptotic or near horizon observer, basically because there's a part of it that's going to be super translation invariant, but it's going to shift both the horizon and the boundary. So the difference between that, in the same way that the memory effect would be the thing that one would observe at infinity, is property 2. The fact that it can be measured by an observer falling in from infinity at the level of the same way you would measure the memory effect versus the zero Goldstone mode C. But then also a little bit about an argument about how like one would make that measurement, because we want to talk about basically decreasing the entropy when you're effectively falling in measuring that. And then 4 exponentially sensitive probes of infalling matter. We're going to see that from basically the commutators of these stress modes. And then 5, that it carries a large amount of entropy. So this is a statement about the size of the soft phase space. And that's a technical statement needed to apply the quantum circuit technology. 6, that when you make that measure, you project it to a low entropy state. So again, this is about the size of the code subspace versus what would be the soft hair part of that black hole state. And then finally, the next thing is accumulate more entropy during the Hawking evaporation process. So that's a statement about how the unitary evolution of this evaporating black hole is acting on the different qubit sectors. So some of them are technical and some of them are more like we need to kind of reanalyze what we actually mean by these like software degrees of freedom. Okay, so this is going to be familiar to all of us basically. The statement is the following. So when I have some sort of scattering process, especially when I'm looking at super translations, then in the process of some loss of energy, so there's energy flux coming from radiation in an inspiring binary system or whatever that you're measuring, you're going to see that that is encoded by basically like the early and late time values of some Goldstone modes that are kind of parameterizing the vacuum. So with a very nice case of super translations, for typical scattering processes, you expect to basically induce vacuum transitions. For super rotations, obviously, that's a little bit like one has to go to like these snapping cosmic string papers or compares analysis, and it's a little bit maybe less obvious the extent to which you're actually dynamically shifting the Goldstone mode. But the super translation case is quite nice to deal with, where basically if I can either think about it as a Goldstone in the memory mode, or I can think about it as basically for every boundary component, I have an early vacuum and a late vacuum. And that like dynamically, there's going to be a non-trivial difference between those two. So I'm going to have essentially an accounting of the different degrees of freedom associated to each boundary. So in the celestial diamond story that Andrea presented yesterday, we basically had two copies of the diamond corresponding to like the one canonical degree of freedom in the phase space for each of the asymptotic symmetries, basically. Like the leading soft theorems had a diamond, the sub-leading soft theorems had a diamond for each of the gauge theories. And so that two copies for us, we want to basically make sure that we're keeping track of, for each boundary component, the initial and final values, so basically the Goldstone memory modes, because a key other aspect is basically when you have a horizon, it's not like one can potentially actually have more degrees of freedom. So basically, let's think about what happens to the soft sector of phase space. And one thing you'll note basically is this would be the analog of whatever I have an operator in my celestial CFT, and I have a discrete label for essentially in versus out. One can also imagine that the appropriate thing to do, which I guess I'm advocating for it, but it's not essential. Essential is if there's like a major complaint about it, it's not going to be essential to what I'm saying. That if you were going to try to compute something in the celestial CFT, one would probably naturally add another label associated to that other boundary component for the same degrees of freedom. And essentially that boils down to the fact that they all are going to shift under these large gauge symmetries. And so you can see how the degree of freedom counting basically goes down, because BMS invariance would say there's like one, like if you all shift them simultaneously, that's basically this asymptotic large gauge symmetry. But indeed, there's still something measurable there. There's still these memory modes. And so then CPT invariance is actually why you don't see this kind of doubling in the celestial CFT, because basically the zero mode at past null infinity is matched to the zero mode at future null infinity. So they're really, even though for the finite energy scattering, you have like a plus and a minus index on the operator, one would expect from the setup with this antipodal matching that when it comes to the zero modes, there's basically going to be one. There's going to be one stress tensor, not the in-stress tensor, not out-stress tensor. So various rough degrees of freedom counting. Now, of course, one can also still look at the strictly pure gauge part of the phase space. But the thing that I'm emphasizing right now here is that in principle, once you have extra boundary components, the standard, even like the very kind of aggressive attitude of saying, I'm just going to like dress everything and gauge fix or whatever like going on, which is rather extreme from the point of view of, we obviously know that there's a lot one can gain by not associating dressings by necessarily having to be on the in state and on the out state. One can have like the radiation come out in the out state, even if you don't dress in the in state. And that's a very nice insight by Strawman, Rick Clariou, and others regarding these like soft dressing papers. So the point of view that I'm taking right now, though, is that think about what happens when you add another boundary. And there, unless you have some sort of matching conditions, say at future infinity, which would be a bit somehow harder to imagine how to motivate it from the same point of view of like what one does at spatial infinity, because basically they're like, you don't want anything kind of weird happening at spatial infinity. That basically you can have this, there's basically essentially an enlargement of that phase space. And so that's going to play an important role from the point of view of if we're trying to talk about basically, if I tether my dressings, or even if I try to set up something that would be invariant under these large gauge symmetries, I still can probe basically another memory effect, essentially, by like saying, what's the value of the vacuum associated to the boundary at infinity, or in particular, my Cauchy slice, I could say future null infinity versus the boundary at the horizon. And in falling zero is going to basically be falling through and carry with them their coordinate system where they've essentially made a measurement. This is going to be the argument for the near horizon part. Okay, so locally, this hair, if I look at, so I have my Cauchy slice, and I'm at an early enough time where basically I don't have any radiation, I can describe the vacuum at infinity as by the value of this Goldstone mode. And if I look at the same Cauchy slice, but over at the black hole side of that nice slice, then I will see that I can't simultaneously kind of get rid of both of the soft hair degrees of freedom. So I can shuffle it around. So one option would be I can basically reset. I can perform a large gauge transformation that for a given early slice where you're meeting whatever conditions in the radiation such that you actually are essentially almost in a vacuum configuration. I can do my large gauge transformation to set it to like the canonical like Minkowski vacuum. But if I did that, then I'd still have non-trivial hair at the horizon and vice versa. And then one way one can kind of resolve that is if one wants to say, well, they have this gauge symmetry, or like basically if I look at just the behavior of the fields at each of these boundary components, I can choose a coordinate system that uniformizes it, but you can't just shuffle that to nowhere. You have to shuffle that into basically a transition function between the coordinate patch you're going to use that would like basically for the early vacuum at null infinity be kind of gauging away the super translation and the same thing at the horizon. You need to put that somewhere, and that somewhere is going to be in the transition function. So this is going to be the sort of origin of the claim that when you're falling through, you're essentially either like parallel transponding or whatever, carrying your dressing with you across that patch, and you're not going to be able to avoid those two different boundary Goldstone modes, basically. Okay, so that's what I say underneath the text. Okay, so then the last part of that slide was uniformizing both so that you're encoding basically the soft hair in a transition function. And so one thing to keep in mind there is that basically if I did say I'm going to try to use coordinates where near the horizon I am just in Kruskal-Sekers coordinates, then I can basically, if I did a super translation symmetry of the Schwarzschild metric in my standard bonding coordinates, or where like basically U and V are going to be this T plus or minus R plus like the R log, like 2M over R minus 1 or whatever, like the standard infalling R coordinate, so that that you get in Schwarzschild. Basically what now I'm going to see is I can essentially put that into how I define the one coordinate patch versus the other. And so what now I've written right down how to go from these UVZ coordinates, or like the U and V I've focused on, to the little U and V null coordinates that have been super translated. And of course, in advanced radial coordinates out at infinity, my Schwarzschild metric is taking the following form, and my Lie derivative is along the vector field as written. So basically, I start with this metric. Say I'm just like literally looking at the background where it is just Schwarzschild. I can take a Lie derivative on this metric, look how it would change. And then if I wanted to, when I'm doing that symmetry, I am not just doing it in one patch, I'm doing it to the full space-time. And so the transition function one would want to use would be related as such with the F dependence in F. And so the first thing to note is that basically, as pointed out in Hawking-Farrier-Strominger, if you have a shock wave or something falling into the horizon, there's going to be some back reaction. And in particular, you're going to implant soft hair. So you're going to change the value of F, basically, or you can use an F dependent, like you can choose a null matter distribution such that you induce a change in the metric that corresponds to a super translation. And in doing so, you're also going to move the horizon a bit. So this moving of the horizon is going to be important because essentially what's happening is that somehow there will be a sense, which we'll see soon, that the Goldstone modes and that phase space, the commutators of that phase space are able to capture what otherwise be these non-trivial back reaction dynamics of like shockwaves crossing horizons, or in other cases, like shockwaves crossing each other. So the key step that's going to happen next is we're going to promote certain of these quantities to operator valued expressions. So let's just take a step back and appreciate what supertranslation is giving, invariance is giving you. So we have normally the standard ward identity is equal to soft theorem type statement. If we would just had null infinity and passing future null infinity, we would have an incoming charge and outgoing charge acting on the respective vacuum, giving 0 in the S matrix elements. And so in that picture, once I have a horizon now, I get contributions from, say I was looking at I'm going to look at the configuration that I showed you a while back, which was this black hole forms by collapse, and now I have a late time horizon. So my outgoing state is going to have a horizon component and a future null infinity component if I kind of hug that Cauchy surface. And then further, each of those guys are splitting into a soft and a hard part. And then I'm already seeing the different tensor factors of the Hilbert space that I would need in this quantum surrogate technology from that HPS story. So the key point to bear in mind there is with each of these charges, you have the hard charge is acting non-trivially on the matter sector, while the soft charge is acting to basically introduce this inhomogeneous shift of this Goldstone mode. So on a given horizon component, if I take the soft charge for that boundary component, then it's constructed such that you can write it in terms of like the boundary data, like so the initial and final values along that horizon, and it will introduce a shift in both the future and the past horizon. And one can see that basically the commutator of f plus and f minus is such that this is the Green's function for this differential operator that's appearing when you're essentially like evaluating the soft charge in terms of the Goldstone modes. So what one can do, and this is not what one has to do, but what one can do is if one wants to create operators that are definitely invariant under supertranslation, so I'm basically dressing my operators, then I can do so with Wilson line type operators. And so basically here, if I have particle with momentum p, and z, for me, a z and z bar is just a little bit of a shorthand, which shouldn't get in the way for this talk. I can have each of my hard operators dressed with a Wilson line operator, which is basically going to have the 0 mode. So I believe, like in my talk at Corfu, and then hopefully this is familiar from the Celestial Diamond story, this f hat would be this C, and you'd see it also in the papers of like Nima and Andy and Malika and Anna, as well as I think Kimwich and others on the looking at the gravitational soft S matrix recently. So what one can do is basically you can put this dressing into this operator by a very convenient just change. Basically, if you promote the frequency dependence, so this is a plane wave propagating through, if you can promote that coordinate to this operator valued guy, you end up having the dressing incorporated, because basically if you do f hat, the operator will shift under the super translation, and so will the coordinate, because as we saw, the vector field basically is introducing a shift in V. So essentially, by taking your operator and having operator valued coordinates, you kind of incorporate the dressing into that, because you're having coordinates that are now compensating for the change in the Goldstone mode.
Now, are these operators you're dressing, are they inflowing or outgoing?
So the operators, exactly. So like what I'm going to do right now is I'm going to talk about how I would tether an incoming and outgoing operator. So in this case, I just wrote the incoming guys with this advanced coordinate, because to not confuse myself for later when I also introduce an outgoing guy that I'm dressing. So essentially what the interesting question is going to be, if I choose to tether my operator to different kind of point at infinity, or essentially which 0 mode I tether it to in some sense, that you can make a choice that such that it captures what would be the Lyapunov behavior of like these commutators, and you trace back like the perturbation caused by the in operator on the out operator, where they would meet in the space-time.
I see. So ordinarily you wouldn't want to address the incoming operators, but you're saying you're doing it to somehow understand this algebra. Is that
exactly? So I'm not saying that one has to address the operators, but I'm saying that if one wanted to even talk about one could set up something so that it is actually super translation invariant, and see from that algebra of the 0 modes that if one does this dressing on what's the remaining phase space, even if you kind of got rid of some of the interesting freedom that you have to dress on the out or whatever, that you can capture this Lyapunov behavior. So presumably because you do have this freedom to shift the dressing around, that this should be hidden somewhere when you don't dress, right?
Thank you.
Great. Okay. So because the commutators of and this is part of the reason why I don't have an extra index on my F plus and F minus, I've kind of secretly been taking my whatever, like 3 boundaries with 2 coordinates each, and then kind of gotten rid of the overall super translation invariance. So I have this F plus and F minus sitting around instead of, I guess, twice that, I think, with just the CPT invariance built in. Okay, so basically what I have now is I have the fact, I don't want to be too quick with maybe how I tether my operators to infinity. And especially if one has a picture where one is talking about kind of like building up the space-time from patches where I have these super translation degrees of freedom, and then I need to solder it together to talk about like the experience of an observer actually moving through the full space-time. Then for a particular choice of dressing, where basically now my operator, the artifact of why this looks a little bit different here is essentially, if I was actually going to infinity, this term, this gamma, I think hopefully I've written it here, or if I wrote it on an earlier slide, gamma I've written here. So basically, if I were actually going out to infinity, that term would, well, wait, but the important thing is going to be the interaction, like basically propagating back where the, a shock wave coming from where the out operator would be and in operator would be. So one can see that if this would dominate in the region where I'm near the horizon. And so as an artifact of basically the coordinate patches where I'm using a patch that extends from past null infinity. So like the V coordinate has a very clean form, but the corresponding U coordinate then is a little bit more complicated in terms of that patch. We have this non-trivial bracket that if you're near the, if you're at the U minus V such that you are near the horizon, this term would dominate and is the following Green's function. So the nice thing about that basically is that once one has these operators that are tethered to different patches, so essentially this is going to be the late versus the early horizon Goldstone modes, that one finds essentially this harbinger of chaos, this Lyapunov behavior of this commutator. And this is again coming from arguing that like these guys are basically going like plane waves where now they have these operator valued frequencies in the phase, and then just using the commutator here and assuming that it's dominated by the term that's largest when you're near r equals 2m. So essentially what the upshot of it for us, okay, so let's maybe first talk about the upshot for the point of view of that paper. And so one can define the stretched horizon where that commutator quantity becomes order 1. And one can also promote this to the case of infalling observers, where basically what you're doing is you're tracing back for a given trajectory where those signals would interact, and using that location to evaluate this commutator between these dressed coordinates. And so what one finds is that basically you can do the same thing for infalling.
How do I understand that Lyapunov exponent diverging when the mass goes to 0?
Okay, so okay, let's be careful here because the gamma out front is it has its m over here, so it's like 0 times it.
Oh,
I think I guess one could be a little bit more careful about like the yeah. So yeah.
Yeah, that's not
right. Okay, thank you.
Yeah, no, I mean, it's obviously like a little bit non-trivial that term is dominating because of like the fact that you're not, like obviously when we tether these operators to infinity, if we're really looking at the large R limit, that term wouldn't even matter. But it's the fact that the interaction is basically like you're propagating the operator in one coordinate patch that's dressed to versus the other one, and you're seeing that those two guys would not commute and have this interesting like back here. So basically the kind of very nice thing about it is that essentially that behavior of the outer time order correlators is appreciated and studied by Herman and others from a kind of different point of view. And so it's kind of very nice that if there's a way that we can massage things or have a prescription for where we're basically tying down our dressings, because our dressings should somehow take into account the fact that there is these different soft degrees of freedom that one has available, that one can make a choice that does reproduce that kind of back reaction effect. So we've seen an example here where basically some interesting back reaction behavior is captured by the Goldstone modes, and that's what I care about for this talk. But of course, for the actual paper that I'm presenting, the key point was that, okay, so now we have this Lyapunov behavior. This Lyapunov behavior is a signal of like catalyzing a quantum to classical transition. I can argue that I'm making a measurement because of that. And then now that I made a measurement when I've fallen through, because I've essentially, like, my observer has to like basically move their coordinate system and they're dressing through to the horizon. So I'm like using some, I'm using basically the lore of like how this chaotic dynamic signals this quantum classical transition to argue that I make a measurement, and then I project myself down to a much smaller code subspace where I can resume the standard page curve. So basically, the key point for that paper was to get to the stage where you have signals of something indicating that one is making this measurement, and then one can then start trying to further apply the machinery to develop this like quantum teleportation protocol. So the step that I was deriving there for this paper was just to get to the fact that I am saying that I'm making a measurement. And then after that, all of the steps for this quantum teleportation protocol are using some assumptions about the size of the soft hair compared to the code subspace of the black hole, and a little bit about the dynamics of how it's evolving. So I'll briefly present that, but again, the emphasis for me right now is the fact that this Goldstone mode, which we all love Goldstone modes, is able to capture some interesting back reaction dynamics. And then can we play with that more? So just to be complete about the fact that I'm presenting a paper as opposed to just presenting random thoughts on papers, I'll outline the rest of that argument for the paper. So basically, the two things we're going to use are that the soft hard Hilbert space tensor product structure and some assumptions about the sizes of those two subsectors, as well as the fact that now with this argument about making a measurement, this observer and soft mode are going to be entangled. And so you basically then can start with an EPR pair of like the observer and the soft mode for a given super translation parameter. So then basically the thing that one wants to show is that the early and late time radiation, so the late time radiation is going to be entangled with interior modes rather than the early radiation, so that basically you can have the right entanglement structure between like things that are being like the Hawking pairs later on in a later stage of the black hole evaporation, so that the horizon remains smooth. And so just very roughly, let's just highlight this quantum circuit technology from Yoshida, where these ingredients that I presented are coming in. So the first thing to point out is the fact that you have some code subspace in this large soft sector of that state of the black hole, that this unitary evolution acts on both of them and is scrambling, is going to go into this decoupling theorem applying. And then the statement about making that measurement is this EPR pair between the observer and the soft hair. So basically this circuit already exists in like some proposal for how one would evade a firewall, but the interpretation of it, oh, this is the soft hair, or this is the observer making the measurement, etc., is coming in, is being like kind of retold in terms of the Hawking-Perry-Strominger story. And so then like at the end of that paper, the kind of upshot is to basically reapply that machinery with this interpretation to show the entanglement structure here for like the early radiation, and then you're distilling it so it's not entangled with this late radiation. So that's all good. And so that's a nice kind of self-contained result in that paper. But the kind of cool thing about it, or the thing that I want to, I guess, maybe leave off as a question rather than an answer, is essentially.
Could you back up one slide?
Yeah.
So, so what you're saying here is that the code subspace has to include is including the soft Hilbert space, is something
no,
that
it's everything else. I mean, and technically we want it to be, I guess, relatively small, but
that's something I would certainly agree with. But is there any? I mean, there's no mechanism here. I mean, there's no. You're not showing that there's a mechanism here.
No.
I mean, we don't know that this happens. That's what we want.
Exactly. I'm not. Yeah. I'm just basically. I mean, like, it's intriguing. I would say it's intriguing, and I would say that it seems better to be able to assign something where you have some intuition for each of the terms and each of the lines in the quantum circuit technology in terms of something that's somewhat intuitive. Now, of course, the thing is the observer, how is it going to be entangled with the full like F everywhere? It's probably only going to see some sort of like patch of the horizon, and then you want this to effectively hold for the part where you're falling through. But I agree. So basically, I agree that it's an explanation of what could happen rather than saying that it has to be that. So it's like, given some assumptions, then this would hold, and this would be a nice HPS interpretation of Yoshida's argument. But it doesn't say that it has to be such that S is much larger than C, or S is much larger. The thing that we technically need for this distilling is that this late radiation is smaller than the soft sector. I mean, I think it's reasonable-ish from like whoever other papers have like tried to argue about like the entropy accounting from these soft degrees of freedom. But for instance, especially we wouldn't want it to be everything, like, because first of all, if you're only falling in, you're only seeing like some patch of the horizon you're falling in, or also there's other Goldstone modes. You don't want to say that like super translations are everything. So it's good that it's a little bit ambiguous, but also not good in the sense that like, yes, we have to claim or assume it. So it's one of the assumptions rather than a something that kind of has to fall out in this.
Gotcha.
Good. Okay. So I wanted to close off with a bit of not a tease, but a moral of the story. So we've shown this derivation where we're trying to say that, okay, an infalling observer, because there's soft hair and that soft hair gets measured by the infaller, that they don't experience the firewall. So that point of view was saying you have this very nice Hawken-Perry-Strominger result. There's a lot of questions one can ask about like entropy accounting or other like black hole evaporation, like actually like what happens in the final state, like whether like why you're think you see a thermal state, et cetera, because you're not measuring soft here. And this is basically saying, I'm going to take this story and I'm going to basically relate it to this very nice stuff that Herman's done in other contexts, and kind of have a nice conclusion from building off of that story. And so in that paper, we kind of see that one can basically use this nice intuition from this Hawken-Perry-Strominger result and try to attack another interesting bulk physics question. And in the process of doing so, what I care about here is the fact that the key ingredient that was coming in is that essentially this soft phase space can encode a lot of interesting physics, precisely because basically these Goldstone modes are kind of capturing back reaction effects. So we saw that this super translation dressing mode could capture the Lyapunov behavior associated to matter falling in through the horizon and the horizon back reacting. And then that was a harbinger of chaos in that context. However, we also know that these dressing modes are the ones that live on top of the celestial diamonds, and they're these heralds of symmetry. They're basically governed by simple toy models for how these vertex operators, what their correlators will look like. You know that they're very highly constrained by symmetries, et cetera. So basically what I want to kind of just close on is that if it wants to pursue this kind of line of reasoning, if you can show that there's a bulk process that's going to be dominated by this asymptotic symmetry group spontaneous symmetry breaking dynamics, then that process should be captured by the 2D effective field theory for the conformally soft sector. So essentially what I'm kind of advocating or kind of closing off is a little bit of a tease for hopefully what will be soon to come upcoming work. But then also kind of the moral of the story of this paper with Herman from December, given like all of the other things that we're interested in, especially in this conference, is that we have a lot more control, I would say, over these symmetry sector of the celestial CFT. So even if one doesn't have necessarily the full celestial CFT, I think there's a lot one can say about the effective field theory for these Goldstone modes for not just super translations, but also the Virasoro case, et cetera. So given, like, so basically I want to set up like the moral here is that if I can use the same bulk version of that dynamics, so whether it's a back reaction effect, like in this case, these shockwave interactions or otherwise, and that's the essence of the physics in the bulk, then I already have control over that in the 2D EFT. And I can try to kind of go through the machinery of the celestial CFT, sticking to the part of the celestial CFT that I have a better control over because it's basically governed by symmetries, and basically reinterpret these interesting bulk processes. So that's basically what I want to advocate for. And I think that I've given enough of a teaser for, or like an example of how it worked in this paper from December. And then I think that it's pretty clear from Andrea's talk that there's a lot more to these effective field theories, and with papers by Neugen and Salzer, and I think Lorenzo earlier, like a lot of people have been understanding these dressing modes and this sector. And basically the only thing I'm adding to the story is it's not just the currents and symmetries in the bulk that are relevant here. There's actually interesting back reaction, quantum gravity effects associated to the same asymptotic symmetry breaking. So that's where I wanted to close off, and thank you guys very much.
Thanks, Sabrina, for a great talk. Any questions? There's maybe one on Zoom.
Let's see if I can see the chat.
It may have disappeared.
Yeah, I might have actually killed my chat. Let me see if I can pull it up. Okay, good. Okay, I don't see it. Okay, I don't see a chat.
We're sort of keeping an eye on it here, but we can't seem to find it anymore. I think it's a dumb question. Can you go back and show us this Lyapunov exponent formula? Yeah. Okay. So sorry, I think I just didn't understand the answer to Andy's question. What do we expect to happen in the flat space limit? Like when M
the
goes.
flat space limit, this should go away because basically there's an M out front here from gamma. The reason why. So essentially what's happening is the following is I'm ignoring gamma because if you look here, so the key point here is it's the coordinate of where those signals from the operator at the 2 points are meeting. So where that interaction would occur is at R around 2M. And so this thing would be basically E, right? But the intuition for what happens when M goes to 0.
It's blowing up.
Yeah.
Why does it beat the exponential it's blowing up?
Oh, sorry. So like
the formula, there's another exponential, right?
Yeah, but there's another exponential out there. So one should be a little bit careful about what U minus let's see, let's be a little careful. Okay. It should not,
so good, just back to okay, we can remember what gamma is, go back to the Lyapunov.
So what I'm saying is that I think one should be a little bit wary of the fact that there's a U minus V here, which in terms of, like, I'm using coordinates that are a little bit redundant, so it's like U, V, and R, that one should be careful that doesn't actually cancel it, but because the limit that I care about right now is where it's order 1, basically, so that's why the grouping makes sense.
Oh, okay.
Yeah, right, because if R is around 2M, then that one kind of is just like 1, versus if like 1 is then worried about like taking like limits where M is going to 0, then right, or you'd also be sending R to, right?
If something funny happens with the U and V coordinates.
Exactly, right. U and V are differ by, well, naively they differ by R, but there's also like R log, whatever, right? Like this, like.
Yeah, okay.
So hopefully that should cancel there. I believe if one were trying to keep the order of limits, and it would just go to 0. So, yeah.
So it's kind of intriguing, this thing of eliminating the dressing by doing an operator-dependent coordinate transformation.
Yes.
It almost sounds as if you could go into some, I guess in quantum gravity, does it make sense? I mean, because the points in space depend on the field strength. I don't know. Could you just, so it sort of sounds like you could eliminate the soft gravitons or even soft photons by, I guess it makes more sense when you're talking
the
about
gravity case, yeah.
By doing field-dependent coordinate transformations. So there's some field-dependent coordinate system in which there's no dressing present. Could you just comment on how we're supposed to think about that?
First, I want to front that I don't think we're the first to do that. Like, I like whether or not, like, when you read the paper, got it from it, but looking back in hindsight, I think that Parati and others have also had something similar. So, like, I just want to, like,
I think this in the early 90s.
No. I'm just saying, like it's. I think it's a nice thing, but I just want to make sure that this is not like we're not like that's not our new thing. It's a nice. It's just sorry. So make sure even in this context is what I'm saying. So basically, I think that the nice thing about that, I would say that, I think in some sense it makes sense because basically you're saying that like you have these coordinates that are going to be not diff invariant. So you're basically building something in that's diff invariant because you're using coordinates that are like operator valued and taking into account those soft modes. So I think that intuition makes some sense, and especially people who want to talk about like non-commuting coordinates and things like that. It's kind of nice. But and especially, right, so it's from like the point of view of Herman, like he's interested in the way that celestial CFT in particular, like you kind of don't see translation invariance manifestly from the construction. I mean, obviously there's Poincare symmetry for these blocks and things like that, but the fact that it kind of comes out of the theory rather than very easily seeing that like the U equals 0 locus is going to it doesn't stay the same under translation. So I think that there's some perspective there where the way that when you put Lorentz symmetry first, you kind of make translations come second, that like building something in where like the kind of the operators are taking into account the fact that celestial sphere that's the intersection of null infinity and the like cone moves might be even favorable from that point of view.
Any other questions? Going once, going twice?
Sold. To the coffee break.
An interesting talk.
Thank you.